Assalamualaikum and a very good morning and warm welcome to all participants to this webinar event. My name is Muhammad Mustaqim bin Hadi and I would like to thank you everyone for joining us for IEEE PES Malaysia Research Discourse 2021 webinar session. Today, I will be today will be the second session of this research discourse and I would like to introduce our speakers for this session. First of all, I would like to introduce Dr. Jiashen Teh, which, who received the Bachelor of Engineering of First Class Honours in Electrical and Electronics Engineering from Universiti Tenaga Nasional Uniten Selangor, Malaysia in 2010 and the PhD degree in the same field from the University of Manchester, United Kingdom in 2016. Since 2016, he has been a senior lecturer or assistant professor at the University Science Malaysia, USM Penang, Malaysia. In 2018, he was appointed and served as an adjunct professor at the Green Energy Electronics Center of National Taipei University of Technology in Taipei, Taiwan. Since 2019, he has been an adjunct professor at the Intelligent Electric Vehicle and Green Energy Center of National Chun Sing University in Taichung, Taiwan. His research interests include probabilistic modeling of power systems, grid integration of renewable energy sources, and reliability modeling of smart grid networks. He received the Outstanding Publication Awards for USM from 2016 to 2019. He is also a regular invited reviewer for various IEEE, IET, and Elsevier journals. Today, Dr. Jiashen will deliver a presentation on his research area titled Network Topology Optimization based on dynamic thermal rating and battery storage systems for improved renewable penetration and reliability. Such a wonderful person.
Okay.
So, for our second speakers for today is Muhammad Lufi Ohman, who received the bachelor degree with honor distinction magna cum laude in electrical engineering from the University of Arizona, Tucson, in USA in 1990, and PhD degrees in electrical power engineering from the University Putra Malaysia in Serdang, Malaysia, between 2004 and 2011 respectively. Currently, he is an associate professor at the Department of Electrical and Electronics Engineering in Faculty of Engineering, University Putra, Malaysia. He is a research member of the Advanced Lightning Power and Energy Research, or the short form is ALPER, in UPM. He also practices as an electrical engineering consultant in electrical services installation works by diversifying as an electrical director or partner in a local engineering consulting firm. Associate Professor TSIR Dr. Lutfi, areas of research interest include, among others, power system protection, such as protective delay operation modeling and analysis, computational intelligence-based data mining for knowledge discovery in relay database, application of artificial intelligence in protection algorithms, adaptive numerical protective relays, development of numerical protective relays, power system operation, electrical services installation works, and energy efficiency management. Today, Dr. Luffy will deliver a presentation on his research area titled Resolving Impasse in Modern Power System Protection, the Knowledge Discovery in IEDA. So today, we'll be hearing topics from both wonderful speakers. So I will pass the session to Ms. Tasmia.
Thank you, Mustaqim, for giving me the floor. Now, I'd like to invite our first speaker today, Dr. Jason, to deliver his presentation on his research area titled Network Topology Optimization based on Dynamic Thermal Rating and Battery Storage System for Improved Renewable Penetration and Reliability. I'd like to humbly request Dr. Jason to deliver his presentation now. Over to you, Dr. Jason.
Okay. All right, thank you, Tasmia, and thank you, Mustaqim, for this wonderful and kind introduction. All right, without further ado, I will start my presentation now. And first of all, thank you for everyone. Thank you everyone for tuning in today in this and share your weekend with us this morning. So today I'm going to talk about network topology optimization, and this network topology optimization will be enhanced by the dynamic thermal rating system and also the battery, right, for renewable penetration. So when we talk about renewable, the main focus of renewable will be wind and solar. All right. A bit of myself. Just now, Mr. Kim has wonderfully introduced me. So this is my background, and I joined USM. I'm from USM, a senior lecturer in USM since April 2016. Okay. So today's my today's presentations will revolve a lot on the concept of power system reliability. And first, I would like to introduce what is power system reliability. So, in terms of power system design, right, network studies, power system reliability means we want to achieve a thermal balance in the network. We want to achieve system resiliency, meaning that the system is able to withstand failure and still be able to perform normally. Okay, that system resiliency, or be able to withstand failure that is imposed onto the network. And then we have system stability. System stability deals with the quality of the power, the signal, the dynamics of things. And also we want to deal with system balance. So demand and load has to be balanced all the time. So when we talk about power system reliability from the perspective of power system, these are the four factors that we normally talk about. And these four factors has been identified by the North American Electric Reliability Council. But when it comes to component, right, power system component perspective, component means transmission line, overhead transmission line, OHL, underground cables, transformers, circuit breakers, and etc. Right? We are talking about we want to upgrade those components, right? We want to increase their rating safely. Again, because if we are able to increase their rating safely, then those component is able to perform more reliably, right? And also more efficiently. And another factor is upgrading, right? Upgrading is slightly different from upgrading in the sense that upgrading means we are adding, right? We are adding certain modification to the components. Whereas in upgrading, we do not add anything onto the component, but we use existing parts of the component, but to rate them higher. And refurbishment is a complete change of the components. If let's say there's any damage, so that will also enhance the reliability of the component. And also expansion. So we add redundancy, that also increase the reliability of the component. So I want to show here two simple graph, right? How these actions can increase the reliability of the component. So on the left hand side here, if you look at the black line, right? The black line represents the four stages of component life, and on the y-axis shows the net present value of the component. So the cost of it, right? So the component cost, right? The cost to maintain the component, or the cost that we want to put into the component for operating it, will increase over time, and that is understandable, right? And that's logic, because as component age, the component will experience more damage more often. So, and then we need to repair it more often, and that incurs costs. And what happens is that if we perform optimal renewal, right, based on any of these techniques, then we are able to suppress, okay, this increase in cost to this blue line, okay, hypothetically speaking. So on the right hand side, we see an additional actions of renewing the asset. So generally, the component, the cost of the component will behave in such a manner. So in general, right, no matter what actions we do to increase the reliability of the component, we are able to bring the cost of the components down. So these are, in general terms, what power system reliability means, right, from system perspective and also from a component perspective. So today's talk will revolve around on the system part of things, right? System network-wide perspective. And in power system reliability, more specifically, we can separate power system reliability analysis into three levels, right? In our research term, we call it the hierarchical level, but in layman term, we can just refer to them as level, three levels. So the first level deals with only the generation system. So when we deal with generation systems, such an analysis is simple, right? Because we don't deal with DC or AC power flow. And when we go to the next level, which is level number 2, then we additionally, right, consider the transmission network. So we need to consider generation and also transmission network in level 2. So when we start to deal with transmission network, then the constraints of this network has to be considered. For example, the rating constraint, the voltage constraint, phase angle constraint, power demand balance, and etc. And also the network topology constraint. All these have to be considered, and all these have to be considered and take into consideration when we perform power flow or optimal power flow. So optimal power flow, then you have two variant, AC or DC. And then you go another level, then we deal additionally with distribution network. So in level number 3, normally researchers don't consider level number 3 because the problem becomes too huge to be solved between the simulation and between a reasonable time frame. So what normally people do is that people stop at level number 2, and for people who are interested in distribution network, they assume that the feeding of power from the transmission network is always available, and they focus only on the distribution network rather than level 3, which considers all the three major components, which is the generation, transmission, and also the distribution. So that is power system reliability analysis. And so based on what I mentioned just now, right, if you look at the power system, we have many components. We have, in terms of generators itself, we have easily, right, in the order of 20 to 30 generators, and then transmission lines, we have 40, 50 lines, and then the connections of those lines between buses are mesh, complicated in a network manner. And then you have transformers, circuit breakers, underground cables, you have renewable power plants, all connected. So all these are huge number of components. And when we deal with power system reliability, we want to simulate, okay, one of the major things in power system reliability is that we want to simulate the failure of this event. So the failure of this event, if you imagine for a while, if you have only two components, right, just take one component for a while. If that component, we assume that it can reside in the success and the failure state, then that component has two states. So in that sense, our analysis is simple. We have only two states. But what happens when we have 100, 200 components? Then the number of possible combination suddenly become very huge, and calculation by hand at this time will be very difficult, if not impossible. So we have to find a way to come around this thing. So to do that, we use what we call the Monte Carlo simulation. So Monte Carlo simulation is similar to agent-based modeling. Maybe some of you are more familiar with agent-based modeling. So what we do in Monte Carlo simulation is that it is a rule-based simulation, right? We have a certain rules. In power system, the rule will be AC and DC OPF, right? In other engineering system, the rule might be different, right? So in power system, the rule is AC or DC OPF. So I just want to point out this point over here. Just like I mentioned, right? When the number of components start to increase, then the possible number of states start to increase exponentially. In what order? In the order of 2 to the power of n. So 2 to the power of 2 is 4. That is when two components there. N is the number of components. When 2 to the power of 10, then the calculation become very huge, right? The number become very huge. So that is the reason why we have to use Monte Carlo simulations, right? So in Monte Carlo simulation, we just simulate the individual failure and success state of the components and take all them together, put inside the rule, and let the rule run itself, which is the AC and DC OPF. And that is how we manage to see how the components interact with each other with various combinations of failures. So quickly, Monte Carlo simulations, there are two states of Monte Carlo simulations, which is the first one is the non-sequential Monte Carlo, and the second one is the sequential Monte Carlo. So in the non-sequential Monte Carlo, we don't deal with time. In the sequential Monte Carlo, we deal with time. So to illustrate how times are considered, right, in this left-hand side, which is the non-sequential Monte Carlo, as we simulate the power supply and the demand levels, as you can see over here, over time, we sample randomly, all right, across the time. We take the sample, this is one sample, this one sample, and this one sample. We take the sample randomly across time. We don't necessarily have to go from the first until the last in a sequential order. But in the sequential Monte Carlo, we have to go through the process, right, from the first until the last in a very sequential order. So when do we use sequential Monte Carlo? That is when the sequence of event is very critical in our study. Okay. So what is the results of Monte Carlo? Normally it looks something like this. So in Monte Carlo, then we have, because it's a simulation based and it's also a experiment, sort of computer experiment, then we have to do many number of trials, right, in order to reach a converged solution. So initially, as you can see, the index, or the measured value that we are studying, is fluctuating hugely, right? And that is the result that is unacceptable, because the result, we hasn't explored enough scenario to calculate the values that we are measuring. So the general idea is that in Monte Carlo simulations, we have to perform huge number of simulations, all right? Huge number of simulations, and allow the measured index to stabilize, okay? In a more scientific term, we call converge. And then as it converge, then we can accept those values. Right, so that is a bit of background for power system reliability, how power system reliability are managed in computer simulation and in practical studies as well. And before I proceed into the main discussion of this presentation, I just want to share that what is the factors that degrade the reliability of existing power system. Okay, renewable integration is one of the factors. So as we want to decarbonize, all right, our industry, we want to reduce carbon emission, then customers, industry, all right, regulators, they are demanding more power, more clean power from solar and wind. Okay, those are good things, but we can't just integrate huge number of those renewables into our grid right now, because that will cause unbalance of power supply. For starter, stability issue, okay, whether our network can cope with it, because renewables are intermittent, right? We cannot control their source, okay? So we have to manage that. So renewable integration is one of the factors, okay, that will degrade the reliability of network. High demand levels, right? As population grows, industry grows, economic run, then demand will increase. So huge demand level puts stress onto our network, that it degrades also the reliability. EV penetration is another thing, right? EV penetration is an upcoming. Many people believe that EV will replace the combustion engine in the future, but the problem is that EV depends on electricity and they need to be charged from the grid. So when we have right now just a handful of people having EVs, that is not a problem when they charge their EV. But imagine when the whole nation charge their EV together at the same time after work, and that will stress our network, that will cause huge dip in our voltage level. And those dips in voltage level will lead to blackouts, right? We don't want that to happen. Aging of power asset. Most of our asset, especially in our country, that is considered relatively young compared to other nations, because our independence is slightly more than 60 years. So what is that? I mean, the aging, the components that we have are still in the order of 50 to 60 years from, I mean, roughly speaking. So at this time, right? At this time, those assets are already in their end of life, and it is almost time for many components, right? Maybe we have to consider replacing them or upgrading them. And the second one is the environmental constraints. We want to expand our network, but right now we are talking about environmental conservations, and we are unable to do that. That will also degrade reliability. Decarbonization, as I mentioned, and now right now we have cyber attacks as well. Okay, cyber physical decoupling, meaning that the management of the cyber network and the physical network of the component of the power network might not be as strong as we think. And then the potential technologies to solve all these are through dynamic thermal rating, network topology optimization, battery storage. So the dynamic thermal rating is one of the solutions because DTR can increase the rating of components, existing components safely, right? Based on environmental conditions. And NTO is to control the topologies of our network, of existing network, to redirect power flows and to enable a more flexible network. All right, that will actually uncovers, right, or relax the power flow constraints. So battery storage is to time shift, right, the usage of renewables. So the biggest advantage of battery is that we can save excess renewable and use it later when we have inadequate power supply. And demand response is to manage the usage of consumer. So we want to incentivize consumer to shift maybe some of their usage to at night when the demand for power is not as high compared to in the morning or during working hours. So to deal with cyber attack or cyber risk, then WAM, so wide area monitoring system, is one of the way to ensure that components are being monitored all the time, and then utility can take informed decision to manage those risks as they arise. So one thing to mention is that power systems are normally huge, right? They span across multiple huge geographical areas. So WAMs becomes important, right? They becomes the eyes and ears for the utility. Okay, and then FAC support, okay, flexible AC transmission system, right, to support the voltage profile, to boost the reactive power supplies of the power system. So all these solutions, all these are potential solutions to solve the above factors that will degrade the power system. And today we will be focusing only on these three technologies. Okay, I want to dive deep now into the concept of network topology optimization. So when we look at a particular substation, right? We look at a particular substation like this one, and we break it down, right? We break it down. This is one substation, and this is another substation. They are connected. So this first substation, it has two bus bar, right? Bus bar number 1 and bus bar number 2. So normally, if we don't consider network topology optimization, they are permanently connected. Okay, they are permanently connected, meaning that the power flow is less flexible in that sense. All right. So if we don't consider this switch as well, the generator is connected to only one of the bus bar. The load, this is the load connected to one of the bus bar. The renewable, this is a wind farm connected to one of the bus bar. The battery. So this is the line, the transmission line, they connect the two substation. So when we don't consider this NTO technology, then we essentially have only one bus bar in each of the substation, right? So the connections of these components and the lines are not what we call not flexible; they are fixed. So when we consider NTO, all right, network topology optimization, then all these switch that I'm showing over here become alive, right? So this switch, we can have the options to switch on or switch off. So by switching on and switching off these switches and the combinations of them creates a new topology using only existing network. All right. So this existing network using new topology will mitigate power flow congestions further, all right, compared to what we have in the existing network without this flexibility. Okay, so this is a fairly complex problem when we start to apply this onto a real network. For example, this is the IEEE reliability test system, 24 bus, right? So when we talk about only two buses like this, okay, one substation and two substations, then the problem seems manageable. But when you start to apply onto a network with many number of substations, then the number of combinations for these switches becomes very huge. Okay, and not only that, we also have to consider the failures of the component. Okay, and also we have to consider the DC and AC OPF of the network. So that is where Monte Carlo simulation has its value, right? The agent-based modeling feature of the Monte Carlo simulation. So this is still, some would say that this is still a fairly small network that is not quite practical. So what about in this sense then? Okay, this is basically a combination of this network 3 times. Okay, combine this network 3 times, then we get this larger network. So then if people says that, if some people think that this network is not practical, then in a practical network, and we consider this an NTO, then the problem becomes even larger. So an even larger number of problem requires requires more, right, the features of Monte Carlo simulation. So as I say here, the solution becomes quite sophisticated, right, due to the huge number of possibilities, right? The failure of the components, the combination of the switches, the AC and DC OPI that we have to consider, and then sometimes we have islanding of the substation, which we have to consider as well. So the order of the problem becomes huge. So the second thing the second technologies that I want to talk about is the DTR system, right? The dynamic thermal rating system. So DTR can be applied on underground cable, overhead transmission lines, and also transformer. But I'm focusing only on the overhead transmission line, right? Why overhead? The word overhead is important because when we talk about overhead transmission line, the line is in the open, right? Is literally above our head, overhead, right? And it's what we can see connecting on transmission tower. Those are overhead transmission line, and those lines are subjected to environmental conditions, rain, solar radiation, wind speed, the wind angle, ambient air temperature. So these weather factors will influence, right, the temperatures of the conductor. Okay, and the influence of this conductor, fortunately, there has been huge number of studies framed under this IEEE standard called IEEE 736 standard. So the IEEE 736 standard consider these weather factors in an equation, okay, in a set of equation to calculate the line rating and also the temperature of the conductor. Okay, so DTR is a more advanced technology compared to the traditional static thermal rating system, STR, right? So in an STR, what the utility do is that they assume a particular set of weather conditions, and these weather conditions they give them a very conservative assumption, and based on this conservative assumption, they calculate this STR value. In DTR, then they don't do this conservative assumption, but they deploy sensors, use sensors to pick up, all right, those weather factors in real time, or maybe use sensors to forecast what is the weather factors, and then use these factors to calculate the rating of the overhead line. And that is what DTR system is about. So apart from IEEE 736 standard, we also have the IEC standard. We also have the degrade standard for OHL. Okay, they are all comparable depending on which one utilities prefer, right? So IEEE is mainly preferred in the US. IEC and degrade is mainly preferred in the Europe, right? And underground cables, as far as I know, because I don't look in detail for underground cable and transformer, as far as I know, underground cable has also one standard for the calculations of its DTR transformer as well, right? For IEEE loading guide, especially on clause 7 and Annex G. So that is DTR system in general. Oh yeah, I forgot about this slide. So what I mentioned just now is actually captured in this slide, but with this illustration is better if I use this slide to explain again, right, the concept of DTR. So as I mentioned just now, right, this is a particular conductor connected on the transmission line, on the transmission tower, right, and this is a zoom in conductor profile, okay, the ACSR, the aluminum conductor steel reinforced, the ACSR conductor of the OHL. So it is subjected to solar radiation, convective cooling. Convective cooling is cooling by wind, and radiative cooling. Okay, so heat can radiate out, and also we have heating due to current flowing. Right, current can create heat as well. So all this, okay, this thermal cooling and heating can be balanced in the equation to calculate the line rating and also the temperatures of the conductor. So that is what IEEE 736 described, right? So as we consider all these weather conditions, the locations, okay, the latitude, the elevations of the conductor, and we use them to calculate the DTR, then we can calculate the conductor temperature. As we know the conductor temperature, then we are able to determine what is the sagging level of the conductor. So as the conductor heats more, the steel will expand. As the steel expands, then it will sag, right? So the maximum amount of sagging allowable is the safety limit that utility enforce, right? That is from the regulation perspective. Conductor temperature limit is from the component safety limit. Okay, so these two factors we combine together and we determine what is the maximum rating of the conductor. Okay, so I just want to point out a study over here that shows that from this study is from the U.S. Department of Energy. They shows that, right, with wind considered, okay, we are able to increase line rating capacity by 35 up to 35%. Okay, and in certain cases, right, 44%. So what we call that represent, right, a significant increment in the underlying unused rating of conductor by just deploying the right technology, which is in this case the DTR system, right? Compared to if we just assume a very conservative set of weather condition in the SDR. So this means that we can deploy DTR system into our power system to have a higher rating OHL or transmission line, and expectedly that will improve the AC or DC OPF, which will help to deliver more power supply to power demand, and that improves the reliability of the network. That is one way. The previous one is the NTO, now it's the DTR. So just like I mentioned, STR, right? So in STR, the word static thermal rating system, meaning that the rating of the conductor is static over time, right? Static like this. And then for DTR, for a small percentage of time, it is very high, for example, in this case. And for a very small number of time, we can encounter that the DTR is actually lower, okay, than the STR. Because in STR, what we do is that we assume the weather conditions, but sometimes the weather conditions can become worse than our assumption. So with DTR, it's not only that we are benefiting from a higher rating, we also avoid rating the line when the actual rating is lower, such as represented in this region, the red region, right? So DTR avoid overheating the line and also avoid wasting the actual capacity of the line. In STR is simple, less costly, but it bears the risk, okay, of overloading and also underutilizing the transmission line. Okay, so the third technology to deal, okay, especially to deal with the intermittencies of a renewable, okay, directly is the battery storage. Okay, DTR has also been used a lot, right, to help to increase the penetrations of renewable. But the thing about DTR is that it cannot time shift the usage of renewable, because DTR has no capability to store excess renewable and then use it in the later time. Only battery can do that. All right, and there are various type of battery. You have in fact, right, hydro dam, right? Hydro dam is a form of is a form of huge storage systems. But in that case, in the hydro dam, we store it in terms of potential energy and water in elevated height. Uh, a more preferred and popular, I mean, right now, a more preferred way of storage is through battery, lithium ion battery, particularly. Why? Because this type of battery, they can react fast, right? They can provide fast ramping generations to help support frequency, and also to deal with peak demand. Okay, so that is the benefits of having battery compared to hydro dam. Hydro dam is huge. Okay, they have huge potential. They can supply sustain long-term power, but their reaction time, their response time is slow. All right, they are not fast ramping. So these two snapshots, I get it from the internet, just to say that battery energy storage system market is expected, right, to reach 9 billion US dollar, okay, by 2025, and in ringgit Malaysia terms, that is about 37 billion ringgit, right? Multiply 4. So there is a huge potential, right, for battery energy storage system development in our nation. And if we were to adopt a high amount of solar, I think we cannot run away, right? We can avoid also the supporting battery energy storage system installation. Okay. Yeah, as I mentioned just now, there are many types, right, of storage systems. A battery fits somewhere here in terms of the response time, right? Battery is about 1 hour. We have high capacity storage like methane and hydrogen, but the discharge time can range from 1 hour to 1 year. All right, according to this to this figure. So from RMIT University, right? So the take home point from this figure is that I want to say battery storage system is fairly fast, right? In terms of the response, it's fairly fast. That is the reason why battery storage system has been the focus point, right, in power system study to enhance the reliability of the system. Because in power system studies, whenever we have interruptions of supply, or when we have a sudden surge of peak demand, we want to be able to respond fast, because blackouts, all right, cascading blackouts, failures, which can lead to cascading blackout, happens between uh, seconds to minutes, and that is the contingency event happens develop between seconds to minutes, and that can lead to blackout. So that's the reason why we need fast ramping dispatch, right, of a backup power supply, okay, in the form of battery. So and the modeling of battery, right, depends on the various factors as well. If you want to do the modeling of battery in our studies, it depends on various factors. It depends on what is our charging and discharging limitation. Okay, whether we have to ask the question whether the battery is owned by the utility centrally, or it is decentralized and owned by a third party. Okay, meaning that it's not owned by the utility. And what is the minimum maintenance charge level that we want to maintain? Okay, that is to protect the safety and also to ensure the useful lifetime of the BSS or the battery, right? And then we also have to consider also the capability of the battery, okay, the energy capacity, the power rating, and the location of the battery on the network, because the location of the battery on the network will influence the OPF. All right. So just want to talk about the ownership and covered over here. So this add on the complexity to our study of our power system if we include battery on top of NTO, DGR, and also the failures, the existing failure and the existing possible failure and success state of the power system components. So on top of all those previous things that I mentioned, right, we still have to consider also what is the power rating, what is the energy capacity of the battery, how is it operated, okay. So that again stress, right, the importance of using, right, of deploying an agent-based modeling in power system reliability studies. Um, so when we combine all these things together, right, the mathematical equation will look something like this, right? Uh, I just show this to show that the complexity involved, right, in the modeling of all these things in computer simulation, and uh, the objective, right, most of the time the objective is we have to deal with the generator cost, because from the utility perspective they want to minimize their costs, right. When we talk about generator cost, then we also have to consider uh, what is the cost of generating the power, of course, the startup cost, the shutdown cost, and also the no load cost, all right. And then when we integrate renewable, then we have to consider what is the cost, what is the curtailment cost, okay, the cost of not using wind and solar power, because wind and solar power, whether we like it or not, they will be generating. When they have excess, when wind and solar generate excess amount of power and we don't use it, that excess power, the wastage of that excess power has a cost value to it, okay, has a money value attached to it, all right. So that is what we call the curtailment cost, right. And and then also we have the load curtailment cost. Of course, when you are not able to meet the demand of the customers, then you have to compensate for their loss. All right, not so much in the residential area because normally we don't experience blackout in Malaysia, but in industry that will represent serious implication, right? So industry. So if let's say the electricity is not able to reach the industry during the time when they want, then they will have implications that have to be dealt with, and that has costs. So we have conventional generator costs, renewable generator costs, load curtailment costs, and we combine all this together, then it looks something like this, right? And we want to minimize all these costs. So and this one I just want to show that how do we actually put all these things together, right? These equations are all conventional DCOPF, right? So for those who are familiar with DCOPF, then this will look familiar. And I just want to highlight several things over here is that the additions of the DTR, the additions of the NTO, and also the additions of the battery, the BSS. Yeah. So in mathematical terms, the implementations of DTR is not complicated. We simply replace, right, the traditional rating with the DTR of the line. So the DTR of the line, of course, we have to calculate based on environmental factors and based on one of the standards that I mentioned just now. And the NTO then is more sophisticated, right? Because we have various switches, right? The switches between bus bar of a substation, the switches for battery, the switches for renewable, the switches for generator, the switches for load, and the switches for the transmission line, and also for the both endings of the line. Okay, so the variable z that I highlight over here, yeah, represents the um, NTO implementation. Okay, and I think the BSS is over here, right? We have the charging constraints and also the discharging constraints for the BSS, and this also for maintaining the considerations of minimum maintenance charge of the BSS, right? So in the previous slide over here, this is objective, right? When we want to make a study power system reliability. The objective is to minimize the cost, but to minimize the cost, we have to consider several things. These are the things that we consider. We have to consider the transmission OHL constraints, right? We have to consider the constraints of the transmission line. Okay, we have to consider the generators and the renewable constraints. We have to consider the battery constraints. Okay, we have to consider the load constraints. All right, and between the OHL transmission constraint, right, we consider the DTR. We consider the NTO technologies that has been implemented. The impact of this NTO has been considered, and then we also have to consider, right, our OHL is whether located in only one geographical area or they span multiple area. All right, because if the transmission line is if the transmission line if the transmission line travels across multiple area, then that will have the different weather conditions will have effect onto the rating, the DTR calculations of the line. And then in terms of generator, then we have to consider the operations of the renewable. It can be wind, it can be solar, all right? And then in battery terms, we have to consider the charging actions of the battery and also the discharging action of the battery. And then we have to consider also the maintenance charge of the battery. All right. So for loads, not so much if we don't consider the various types of load: residential, industrial, consumer, government, large user, the types of user. If we don't consider, then and we lump them all together, then load point consideration or load point constraint is not as sophisticated. And then these are the things that we cannot avoid, which is the phase angle constraints, right? Regardless of what we do in the network, we have to maintain phase angle constraint. Okay, and this is only a DC OPF, right? It's not AC yet. If AC, then we have to additionally consider the voltage constraint. So and then the power flow constraint as well, right? Just now it's just the constraints for those components, and then we have the power flow constraint, right? In this case, it's the DC OPF, right? DC OPF. So in power flow constraint, basically we are interested in having the balance of power between supply and demand, and that's it, right? That is the objective of power flow. We want to balance it. So because of NTO, right? Because of NTO, that split a particular substation into two bus bars right now due to the switch that I showed just now. Now the equation doubled, right? The equation doubled. In the traditional OPF, you only have this one equation, but because of NTO, then we have two bus bar now. We have to balance two bus bar for each substation. Then we have two sets of these power flow equation OPF, right? And then we have to consider also what is our limitations of our simulation. Is it n-1 or n-2? So n-1 or n-2, the number 1 or 2 means that if we talk about n-1, then we say that the power system is able to withstand one failure and still perform and functions normally. Okay, if you talk about n-2, which is more preferred because 1 seems a bit too optimistic, and n-2 seems that we are more well prepared, right? So in n-2, then we consider up to only 2 failures at a time. So meaning that whenever there is a 2 failure situation, then the power system can still operate normally as it is without any interruption to the supply of power or to any operations that we have in the network, right? So that is n-2 constraint. So all these constraints we have to consider when we perform the studies. So putting all together, it looks something like this, right? This is just putting all my words in the figure, and I just want to share a bit of share some result from my studies. So I perform 2 sets of studies. The first set is that I compared the effects of DTR, battery, and then the combination of DTR and battery with the basic scenario. The basic scenario is our base case, which we have wind integration inside. I integrate wind. I don't use solar because I have the data for wind, so at my disposal. So I just use wind integration. We can also equally study solar integration. So it shows that, right, this result shows that DTR, BSS, and the combinations of them reports improvement, right, in the generator dispatch cost, load curtailment cost, and also the wind curtailment cost, right? So it has improvement. It shows, meaning that it shows that this technology has an effect, right? But their effects are different. So another set of studies I do is on NTO, right? I additionally integrate NTO inside, and then I also consider NTO and DTR, NTO and BSS, and also NTR and DTR and BSS. This is the ultimate solution. So this is to show that uh, the studies over here with DTR and BSS is better than having only NTO alone, and also to show that the proposed solution is better than the case where we don't use NTO. That is to show that although DTR and BSS is beneficial in terms of uprating and time shift renewable power, um, the the presence of NTO additionally mitigate power flow congestions simply by rearranging the topology of the network through clever switching of the circuit breakers, right, or the switch between the substations for the generators, the line, the renewable, and the battery. Um, so I just quickly go through this. Not enough time now. So this is just to plot everything together from this, right? From everything together. And the green color one is the proposed solution, right? NTO, DTR, and the BSS. Yeah. So it shows that it is the lowest in the three costs that we mentioned just now. A bit of comments for the result is that although the DTR system, right, enables higher delivery of power flow, the higher power, right, may come from either generators or wind farms, right? Thereby, when the amount of power injected from the conventional generator is high, then the power injected from the wind farm, okay, or solar farm will reduce. But the purpose of integrating renewable is that we want to maximize, right, the usage of the renewable, or to minimize their wastage, okay, when they generate power. So with that, we have to complement the disadvantage over here with BSS. So BSS, it shows that it can complement, right, this weakness of the DTR by directly time shifting the power dispatch, okay, and of the renewable. So as we are able to save this unused renewable power to be dispatched in a later time, then we naturally, right, rely lesser onto our conventional generator. So conventional generators are normally fired by coal or gas, right? So those are uh, carbon emitting generators, and we want to reduce carbon emission right now. And so it is obvious also that the proposed solution outperforms, right, only if we implement the NTR. So in all the three courses, we are able to see that there is an improvement, right, in the proposed solution. Um, this is okay. This is to zoom into on. This is to zoom into on one of the two buses. Okay, to show how NTO works. So this is the basic case, and these two are when NTO are implemented. Right. This is NTO only, and this is NTO with DTR. But I want to say that if you can see, right, with the NTO, right, this single substation is split into two, and this single substation is also split into two, right? And this particular wind farm, right, if you don't implement NTO, then it is fixed, right, onto this location. It can't change, right? And this particular wind farm is a simplification, right? It is actually a collection of multiple smaller turbines. Yeah. So when we split this wind farm due to clever switching of the circuit breakers, then we separate this into bus bar 1 and bus bar 2. And we can also switch the connections of the wind farms, right? We separate the turbines into uh, bus bar 1 and bus bar 2s, right? So the selections of the switches are all solved, right, by optimization algorithm, right? And this is the same as this, but with DTR, right? So to show that with DTR, we are able to further enhance the rating and enable higher integrations of renewable. And this result is to show the effect of BSS, right? The effect of BSS onto the total cost, right? As we vary the energy capacity and also the power rating of our BSS. So in simple terms, this figure shows that as we vary the energy capacities and the power rating, then the total cost will be influenced. But it shows that, right, the slope of this plane is mostly influenced by power rating. Okay, it's mostly influenced by power rating because the slope of the plane is steeper when we look from the perspective of power rating. So this shows that if we can only choose one of the factor to be prioritized, then we should focus our effort on the power rating of the BSS. Okay, power rating dictates, right, how fast the power can be dispatched, right? The rate of the power to be dispatched in an hour. That is power rating. Energy capacity is merely the storage space, right, of the battery. So the conclusion is that NTO, DTR, BSS have been combined between a single assessment framework as I presented just now. And employing such a method requires a synergistic effect of this technique to be considered, right? So this synergistic effect that I mentioned here refers to the various operating criteria of these technologies on top of the underlying failure behavior of the components, the transmission line, the transformer, the generators, load don't have failure. So we have to consider all those things together. So these are what we call the synergistic effect have to be considered between a single framework. And then the model presented, right, can help utilities to schedule the grid more economically to draft effective strategies for large-scale integrations of wind farms or PV for that matter. So that's the end of my presentation. And I pass it back to Tasmia and any question from the floor, maybe. Thank you.
Thank you so much, Dr. Jason, for this wonderful presentation. It was really very interesting and it was very interesting and enlightening. I'm sure there are many questions from the participants today regarding this presentation, but we shall wait until the end of our second presentation today, and then after that we will conduct the Q&A session. Right before we go to our second, thank you, Dr. Jason. Right before we go to our second speaker, Dr. Lutfi, I'd like to introduce some brief information on IEEE Power and Energy Society. I'd like to show a video about Power and Energy Society now. Thank you. Thank you so much for watching the video. I hope you all enjoyed it. Now, I'd like to invite our second speaker today, Associate Professor Dr. Mohammad Lutfi bin Uthman. Dr. Lutfi will deliver a presentation on his research area titled Resolving Impasse in Modern Power System Protection, the Knowledge Discovery in IED Way. I'd like to humbly request Dr. Lutfi to deliver his presentation now. Over to you, Dr. Lutfi.
Right. Thank you very much, Sister Tasmia Rahman. Assalamualaikum warahmatullahi ta'ala wabarakatuh, and very good morning to all of you. It's really a great pleasure to be here with all you guys, to be invited to share a little bit of things that I've done in my research. So let me share the slides that I'm having with me. All right. So the next talk, which I'm going to present, simply about power system protection. So it's basically talking about resolving impasse in modern power system protection. And we are going to look at how IED, intelligent electronic device, can be a great use in discovering knowledge or behavior of the device in order for us to actually solve some issues in power system protection. And particularly in my talk is about power system protection performance analysis. So I'm basically from a research group called Advanced Lightning Power and Energy Research, ALPA, in Institute Putra Malaysia. Okay, I'll just skip this list of contents. All right. So in a nutshell, we have this electrical power system. It's quite common to most of us. We have a complete set of power components, as Dr. Jason has already mentioned before. We have power electrical components. We have power generation plant. We have substation where we have a step-up transformer. We have transmission lines. We have another substation. We have a step-down transformer to actually step the voltage down to much utilized levels of medium voltage, 33 kV or 11 kV, and much lower low voltage of single phase 230 volts or even three phase 400 volts. So related to what I'm going to present about power system protection, if you were to actually locate some of the devices, IEDs we call it, intelligent electronic device. For example, one of them that is very familiar for transmission line protection, we call it as numerical distance protective relay. We would normally locate one at one end of the line, which is in one of the substation. Particularly in this one is shown as that located near the power plant. And of course, we have one right at the very end of the transmission line over a distance of possibly hundreds of kilometers away, possibly, far away from the first one. We have another one possibly similar distance protective relay located at one of another subsections here. So what they do, basically they interact in a way of coordinated manner to actually operate protecting the transmission line for whatever kind of faults, wherever it is actually exactly located near or far away from any one of them, where this device would simply detect and operate by giving out the tripping signal to circuit breakers to finally open whichever transmission line that is found to be faulty. So that's basically the function of one of many protective devices, and we are looking at distance protective relays. What we are really interested in this seminar is actually to understand the performance of this relay, right? We want to analyze its performance, whether it's operating correctly or otherwise. So in order to do that, there's a particular strategy that we must be well aware of that involves these three steps, which is to hypothesize, meaning hypothesization is simply to actually extract knowledge from the from the protective relay of interest that we are going to analyze its performance. And then once we have got the knowledge, we have got the algorithm, we have got the, in our case that we are going to talk about is simply rules, prediction rules or decision rules of the behavior of the relay. Then next, what we want to do is to validate. So we are going to use the rules to actually validate the performance of other relays, other unknown relays. And then to see whether it's operating correctly or otherwise. If it is actually found to be incorrectly operating, then we are looking at either it's misoperation or maloperation. Misoperation meaning it's operating wrongly. Maloperation operates also wrongly. So we are going to diagnose for whatever symptoms that we might come across to actually see what really has actually happened to the relay. So again, this is about basically looking at the analyzing the performance of the relay. So why we have protective relay? We need to eliminate faults, right? So fault that is found in transmission that I've just mentioned about, or even in the distribution system, is a much lower voltage level, like medium voltage or low voltage. We need to really actually eliminate by first detecting the fault, identifying where exactly the location is, and then we could also possibly classify the type of faults that has occurred. So why we need to do that? Because we want to clear the fault out of the lines, so that we can finally repair. We can correct the situations, so that eventually we would restore the power system back to this original healthy state. So protective relays. So these are just a basic discussion on how protective relays operate. What they do, it would give tripping signal to circuit breakers to isolate the faulty section. Essentially, by doing so, it would minimize the equipment damage and safety hazard of the faults to human being, to equipments, and all sort of things. And of course, to finally maintain the power supply continuity and health. So the relays must do so reliably, in a reliable manner, selectively, meaning it's only operates where it is actually expected to operate, and rapidly, meaning it has to really operate in compliance with the required time frame. So why it is really important? Because failure on the part of protective relays would really, be disastrous. It would spell injuries to human and damages to properties. There are issues with protective relay operations. Inaccurate and slow and even insensitive fault detection and subsequent elimination of faults have been basically familiar constraints in the operation of relays. For example, distorted or erroneous current transformers, or even potential transformers, or sometimes we call it voltage transformers, VT or VT. And then complexity of power system networks, possibly because inappropriate protective relay setting, high fault impedances, deterioration and loss of communication channel that is normally nowadays we use for coordinating the operation of various protective devices, so on and so forth. So there are quite a number of issues that you may come across in as far as understanding the performance of relay. So it has been mentioned by one of the makers, brands, very famous, familiar to us, SEL, Schweizer Engineering Laboratories. It has been reported that 4.6% of relay operations account for incorrect operations, or we call it misoperations. The relay operates, but it's operating incorrectly, so we call it as misoperation. And then whereas as far as mal-operation, which is basically failure to operate, it has to operate, but it does not. So it accounts for almost like 0.91%. So you may look at it as rather quite little in as far as statistics is concerned, number is concerned, but you are talking about protective relays, preventing us from a disastrous situation. So the effect of such a small number of misoperation or mal-operation relay can be so much detrimental to the safety of the power system. So a case in point, because of the incorrect operation of protective relay, we see there's one major blackout that has already occurred back in 1996. It's really a very bad national blackout that has occurred in Malaysia. Well, it's basically started off, seems to be quite trivial, from a compounding effect of failed circuit breakers and simply a misoperation of some backup overcurrent relay that was wrongly set. So you can see the issue here is a wrong setting of the overcurrent relay. But this has basically resulted in a major problem. It has caused the isolation of the IPP's interconnections. IPP is one of the power generators in our country that is providing a bulk of the power supply to the electrical power system of the entire nation. And subsequently, there has been huge swing in the power system. When that is happening, finally, some cascading tripping of power protective relays, and eventually the national blackout ensued. So that's what has actually been our experience before, simply because of the wrong set of overcurrent relay. So one of the protective devices. We are now actually looking at a distance relay. Overcurrent relay is just another type of relay, but somehow both are mainly for protecting the power system against faults. So we need to have analysis strategy of the power protection performance. So there are goals in doing so. One, we need to ascertain its operation, the operation of protective devices or protection system in a wider aspect. We need to maximize its availability, the protection availability. And of course, we need to minimize the risk of relay misoperation. So this is actually the goal of having us to actually deal with performance analysis, analyzing the performance of the protection relay. So the strategy in analyzing protective relay is by way of validating its correct operation and thereafter diagnosing its misoperation. First, we validate if there's a correct operation that is okay. Otherwise, if it's a misoperation or maloperation, and in that sense, we need to diagnose. So we need to understand what sort of symptoms rather that we can identify so that we can do an appropriate diagnosis. Okay, some analysis strategy, and as far as protection performance, we need to look at some of the questions here. In order for us to really come up with a good strategy analysis, we need to really do a bit of research and understand and ask us all these possible questions that are related to protection operations, that are related to fault disturbances that we want to, the protection that we want to validate, we want to diagnose. I may just read one or two of them. For example, what was the state of the protection system in the time of the disturbance? And then was the fault in the expected zone of operation? Did the load flow agree with the system data? And then it goes on and on with so many questions that we might need to actually look at. For example, there's one about setting. Yes, this one. Were the protective relays connected correctly and set correctly? So this again, it reminds us the previous slide where the igniting point of the huge national blackout was actually the wrong setting of the relay. So there are so many questions that we might actually want to ask about protection performance. So this brings us to what we call as automated protective relay performance analysis. So we have already known what the strategies, the questions we want to ask. So how do we understand in dealing or addressing with all these questions? So it is actually the purpose of this work is actually to automate the performance analysis. So what's the strategies like in automating the performance analysis? One, first you need to extract and manipulate the data that is resident in the relay. Why we need to do that? We need to discover, of course, the knowledge, the behavior of the anticipated operation, the operation characteristics of the relay. In other words, we want to understand the hypothesis of relay operations. Hypothesis meaning the behavior of the relay itself. And then after that, once we have attained the knowledge, and then we want to derive the actual behavior of the relay. So these are basically about behavior of the relay, the algorithm of the relay, the operation characteristics of the relay. Thereafter, after gathering the knowledge, after extracting knowledge out of the, as the title goes, IED, which is a distance relay which we are interested in, we want to validate whether the protective relays, possibly of unknown relays, operate correctly. So what we do is that we validate this unknown relays by comparing this hypothesized knowledge with those, or rather with the behavior, or rather with the operations of the unknown relays that we are interested in analyzing. And then, of course, after validating, we diagnose for whatever possible misoperations or maloperations that have occurred out of the relays. So in as far as this strategy, it has been actually called upon by this North American Electric Reliability Corporation, NRC, the same I think council that has been mentioned by Dr. Jason in his talk just now. It is mentioned by them that to determine whether a protective or rather protection system operation is appropriate, it is really actually necessary to compare the observed behavior of the protection system with the expected behavior under the power system conditions in effect. So we are talking basically about comparing the knowledge or the behavior of the relay that we already discovered earlier on with those behaviors of relays that we want to understand their behavior, their operations. So if it is determined that the protective system of operation was incorrect, then the analysis for cause must be documented and appropriate remedial, meaning we need to understand the symptoms, we need to deal with the situation, we need to take up some remedial actions to actually deal with the problem of the misoperation or maloperation of the relay. So this brings us what we call as a retrospective analysis. Basically, we verify in a retrospective analysis, we verify the fact that all elements of the operating system was set properly, operated as we anticipate. And retrospective analysis is very cost effective. We just simply making use of the data available in the intelligent device, and all the we can make full use of the event report in the device, and all the data, the information that is available resident in the relay can be used for valuable for the performance analysis purpose. So it now brings us to this idea of how we can basically automate, how we can basically run this intelligent performance analysis of the protection system or protection device in our case now. So we have intelligent techniques in combination with the recorded protective data. This is rather simply a current state of the art, right? So in the last 20 years or so, automated analysis research has advanced, charting into two primary causes, which we cannot separate. One is using computational intelligence. Another one is using the devices themselves, the intelligent electronic devices. In our case, we are dealing with a distance protective relay. So it's a combination of soft computing and the protective relay themselves. So various computational intelligence techniques have been extensively explored and successfully implemented because why we need to use soft computing? Simply because protection system is simply non-linear. It's a wide scale, it's a huge system. I mean, it's integrated, it's a interconnected protection system. They are well communicated between all, each others. And it's basically an collection or amalgamation of integral subsystems. When you are talking about a wide, system-wide protection, you are talking about many devices in integral, which are integrated to be performing its operation. And if you are even looking at the device level itself, you are talking about the multifunctional units within the protective device itself. So it's actually an integral integration of various functional units. So that's why using computational intelligence is really very much necessary in this sense. So I think some of you might have seen what sort of computational intelligence or soft computing we might want to call it also, used in validating and or diagnosing the protection system. We might have seen expert system, artificial neural network, fuzzy logic, genetic algorithm, so on and so forth. Rough set theory and decision tree are basically the two things that I'm going to specifically talk about, that we are my interest in this presentation. And apart from these CIs, computational intelligence, what are the IEDs that we are looking at? There are many possible IEDs that we can get the data from. We have digital protective relays, right? We have digital fault recorders. We have sequence of event recorders. We have remote terminal units in the SCADA system. We have whatever other IEDs specially used for monitoring and control appliances like automatic recloser and many other types of intelligent devices. We have fault locators. We have synchro phasers, or nowadays we call it as PMU, phasor measuring units. So these are some of the IEDs that we can think of to be integrated with CIS for us to, to help us in analyzing the performance of the relays or protection system. So why? In as far as utilities perspective is concerned, why is it really necessary for us to have protective relay performance analysis? Protection engineers are suffering nowadays with so much of data, huge amount of data. So to actually make an analysis out of such a very complex data is just uncalled for. It's just so difficult. So that's why, because we are looking at, there are diverse of IEDs, as I've mentioned in the previous slide. Data can come from various IEDs. And it's really a monumental task to collect, to file, to manage this large amount of data. So one way to actually help the engineers to deal with such a large amount of data is to just, why not we just focus on device level of the digital protective release alone. This would provide an immense help to the protection engineers. Why? Because instead of looking at all the other devices, from digital protective relay alone, we could make full use of the event reports that we can gather from the device, of all the stock record of what this device has seen of the power system, of what this device already behaved as far as the fault that has been detected in the power system. And the report can come in various formats, either proprietary, depending on the make of the device, SEL, ABB, Schneider, Arriva, GL Storm, so on. There's so many of them. Or it comes in a very standardized kind of IEEE ComTrade format. So this is what we are going to deal with in this particular presentation. A very rather standardized kind of data that we are going to look at. So how do we use this data? So we need to use data mining. We need to embark on using data mining. We need to choose the correct one so that the intelligent analysis techniques can be imposed on the data. All the data that are found, like the fault reports, the event reports, the oscillography waveform report, like voltage, data like voltages and currents, and even the setting of the relay operation characteristics themselves. How can a protective relay data be useful? Of course, as I've mentioned, there are all sort of values, parameters, quantities that we can extract from the report. The voltages, the currents, the inputs, output contacts, or even of other devices like circuit breakers. The various functional elements within the relay themselves, and the current transformer, potential transformer, the type of faults, location of faults, even the apparent fault resistance, or the fault resistance themselves, fault impedance themselves, can also be known to the engineers who want to actually make full use of the data. So that's why the data is very important. Well, ComTrade, talking about ComTrade, IEEE ComTrade data, you may get this ComTrade data in one of two ways. You may run a simulation out of the EMTP power simulation tool, electromagnetic transient program tool, which you are actually able to run a power system together with whatever protective devices along with them, and then you extract the ComTrade data out of it. Or you can also get the ComTrade data from actual recorded events from the actual devices at the substations. With this data, you can play back over the model relay, or even the actual relay found in the substation, to see how they perform. Well, playing back the data, the ComTrade data, is very useful. The purpose is actually to recreate the actual model system event to mimic the severe, critical, or abnormal power system transient conditions. And by also doing so, we can also understand the possible inadequacies that we can find in the protection system. So again, we can play back the contract data in real relay or in model relay, depending on our research purpose. So this is what I'm talking about. Simply in one of the TMB laboratories, we have the model power system, the model relay, and we have basically the Comtrade digital transient record that is played back by this rather, I would say, an expensive test system that only found in utility company like TMB. We as engineer researcher, we don't actually we cannot afford to. That's why we go to TMB laboratories to actually help them. So this playback test set, Omicron CMC 256, is actually able to inject the secondary value of the voltage or currents that have been provided by the model power system into this actual relay. So this actual relay, Arriva MICOM P441 distance relay, or you can also, instead of actual relay, you can substitute it with our own model relay. So what I'm going to talk about is simply the relay that we are going to deal with is simply actually a model relay. I'm going to present later. So, okay, again, back to CI, there are so many of them. You can use singly or in hybrid formation together with the intelligent devices. And as far as expert system, it has been around back in 1980s. It has this if-then rules, but as it is, expert system is not that easy to maintain, simply because to come up with updated or revised if-then rules is just so difficult if we were to actually do it manually, simply because the power system topology is ever changing. The power system protection schemes are ever changing, and you are talking about multiple protective relay functions. So it's just sometimes very much difficult to use expert system. Artificial neural network has also been used to actually help engineers to understand the operation of power system, or even to help them decide the activities of the protection system. But the thing is with ANN is that it has this black box nature. It has hidden layers. Some of you might have known this. This really provides the impossibility for us to actually understand really how the relay behave, because there are no rules that artificial neural network can actually provide us with. All right. And then we have fuzzy logic. Again, fuzzy logic is dealing with fuzzy rules. Fuzzy rules is something that you need to update over and over depending on the situation of the power system and the protection system that is in place. So again, to deal with that is not easy. To update, to basically revise the rules are not easy, simply because the challenges, you need to really understand. You must be an expert of the protection system so that you can really design the correct fuzzy rules. And you have to, to deal with so much information that you need to gather from manuals. Manuals are just so thick documents that you need to really run through so that finally you can come up with a good fuzzy rules. So that's just difficult. We have generative algorithm that has also been used. So I'm going to use generative algorithm to actually help me in finding the decision algorithm of the relays that we are going to discover, and help us in finally designing at the end of this presentation the expert system that I'm going to reach at. So there's a state-of-art synergy, CI and IEDs, GA, and then we have other type of strategies you might want to consider on power system protection, operation, as well as analysis, event tree analysis, and then we have model-based reasoning, right? And of course, decision tree is one of many benchmarking strategies when we are talking about the algorithm, when we are talking about decision rules or prediction rules, for that matter, in as far as protection system is concerned. There are many types of algorithms. So I'm going to use decision trees as benchmarking strategy to validate the technique that I'm going to talk about, that help us in understanding the operation of the power system. So I'm just going to skip that. Okay, a bit of data mining. Why is data mining very crucial in our research, understanding the power system protection analysis? Well, data mining is computational intelligence, of course, in the knowledge discovery in database. We are talking about KDD. The intelligence part is actually to invoke this data mining. So the data mining process that I'm going to talk about is simply dealing with these three types. The rough set theory. I'm not sure whether you have heard about this. It's not too new, but not too old also. But it's a mathematical formulation that is very, very strong in dealing with huge data that is inconsistent, data that is uncertain, data that is not continuous, or data that is there is so much of uncertainties in data. And GA is very familiar to us. And then also rule quality measure. So I'm trying to actually to integrate these three strategies: RST, GA, and rule quality measure, or RQM. So by integrating those strategies, CIs, in the data mining, I'm going to do basically one of these strategies to basically to come up with the solutions, to come up with the algorithm that we can extract from the device. So apart from that, the data mining is also very much useful for prediction, for classification, regression, clustering, association, so on and so forth. This is an overview of what makes up the knowledge discovery in database. In database, in our sense, is actually event report of a protective device. So it would cover things like preparing the data, selecting the data, pre-processing the data, transforming the data, and when the data is transformed, you data mine it to find a pattern. So the algorithm, the decision behavior, or rather the behavior of the relay. So this way you can interpret. Finally, you can make use of the knowledge that you have discovered to be to be formed as a knowledge base for whatever purpose that we can use it for. So in our case, this will be an expert system that we are going to design by making use of the knowledge that we have already discovered from the relay. RST, just in a nutshell, is something very powerful in dealing with the uncertainty, inconsistency, vagueness in data. It's useful for feature extraction, useful for finding which data is very significant. It can be very useful in removing those data that are of no use, right? In reducing data. And of course, what of our great interest is how RST, rough set theory, can be very much useful in discovering the algorithm of the relays, these decision rules. Why this rough set is very much suitable? Why rough set suits the bill in resolving the conflict that we find? Because when you're talking about potential relay, there is a little conflicts in as far as data. There's a little inconsistencies in data, because you at one point you see some conditions have been met for the relay to operate, but no tripping signal has been given out. But some other time, similar conditions are discovered, but the tripping signal has been asserted to actually trip the circuit breaker. So you can see there are inconsistencies in as far as the data that of the event report that you may find in the relay. So this really makes RST to be able to deal with such a situation, inconsistencies in the data. And I'm going to use GA also to help finding or help the rough set theory to finally come up with the best rules, precision rules. How it does is that RST would first reduce the attributes, reduce the data to a much manageable set of attributes. And of course, it is still large as far as our analysis is concerned. So GA will help actually to even reduce that further. By doing so, it can even come up with much better results, which is rules. GA will be helping rough set theory to come up with what we call as minimally approximate hitting cells, meaning meaning hitting sets, meaning the optimal number sets of attributes that are good enough for us to be using them to design the decision rules or the algorithm of the relays. And finally, I'm going to employ this rule quality measure, which is actually a statistic strategy to finally, out of all the possible population of rules that we have already discovered earlier on with rough set theory and GA, now I'm going to zoom in. I'm going to single out one pertinent, one particular useful and interesting rule that tells us the entire behavior of the relay, one single line of rule by using rule quality measure. So this is just a little snapshots of understanding the fundamental concepts of why RSTs and GA and RQMs are so important in this research in as far as data mining approach to hypothesize, to extract data, to understand the behavior of the relays. So rough set theory has been found in many other works in power system, right? Alone, on its own, or maybe in combination with others. But not much has been basically found in the research of a power protection system, and particularly at the device level. You may find not that many or so rough set theory that has been used in system-wide power system, and not so much you may find in at the device level understanding of the protection system by using rough set theory. And of course, none has ever attempted to use these three in combinations. Why I don't just simply use them, but for the characteristics of each and individual single of them that can actually help us in finally come up with the understanding of the relay. That's why we use these three in combinations. There are problems with understanding the behavior of the relays. We deal so much, most of the time, with the expert knowledge. The engineers, the protection engineers, they have different ideas. They have different understanding of protection system. Of course, the fundamentals is the same, but the way that they want the protection system to be operating may be different from one person to another. And of course, you are talking about so much amount of manuals that you need to really churn out to actually understand the power system. So it's just so difficult. That's why to understand the behavior is just in this sense very difficult. Especially when you want to maintain the rules. When you are designing an expert system, you want to maintain the rules, then you need to go back to the protection engineers. You need to study the manuals again whenever there are changes in power system, whenever there are changes in the setting, even the concept of the protection system itself. And most of the studies have been basing on mostly other recording devices in other IEDs, like digital fault recorders, sequential event recorders, remote terminal units on. Not so much, data has been actually gathered from the device alone, the digital protective relay alone, to actually really understand not only the device behavior, but also much wider aspect of the power system itself, that especially those that managed or controlled by the protection device. And DPR, digital protective relay, can hold so much of information of its own as well as the entire power system. So that's why we are interested in just dealing with the event report that we can extract out of the digital protective relay. And I've already mentioned manually extracting knowledge by just liaising the expert that are having differing knowledge, and even so much amount of manuals is just so really heavy task to actually do. So that's why it brings us about this objective to intelligently discover hidden relay decision algorithm. So we're going to actually discover the hidden relay decision algorithm intelligently. And then subsequently, we want to single out one pertinent association rule of this large amount of decision algorithm that would tell us the exact behavior of the distance relay. And we do that by analyzing the recorded event report. So the entire process is called knowledge discovery in database, where data mining will be the most integral part in this strategy. So how do we do that? Okay, how do we do that? Let me see. Okay, this is the strategy. What we're going to do, we would first model the power system using PSCAD, and then we model the relay of Arriva MICOM of P441 using PSCAD also. So what we essentially doing here is that we are trying to model the relay as much as possible, mimicking the exact relay that we find in the industry, Arriva. If you might have known, Arriva now has been bought over by a much larger company, GE Alstom. So it has been rebranded. So this is based on back in those years where the name is still there. So one of the devices, the distance protective relay, is P441. So that's exactly what we're going to model. We study the manual, we study the operation manual, the maintenance manual as much as possible, so that as much as possible we could possibly model relatively close to the exact one that we find in the industry. Why we do that? Because we want to get the data that is resident in the relay to be as complex as possible, because we want to see how good this data mining strategy is in reducing the data to a much manageable size, so that eventually would help us in the process of understanding the relay. And then next, the model, power system, and relay will be tested using the Omicron test set for us to validate the model. And we compare that with the device, the actual device found in the TMB lab. And then we do data processing strategies using a tool from National Instrument called Diadem. It's a Visual Basics based tool to select the data, to pre-process the data, to transform in a way of constructing, discretizing, and simplifying the data to a form that is readily available for the next step, the main purpose of the work, which is the intelligent data mining, which we start off with, gathering the data into the system and feed it to a tool that is called Rosetta. So Rosetta is actually a tool that is specifically designed, is actually a product of PhD work by one of the students of the founder of the rough set theory itself. The founder is named Paulak from Poland. He's a Polish. So the student has designed this Rosetta. So I've used this software to actually run the rough set theory to data mine the data. And then the data will be, of course, the characteristic of rough set theory is what we call as a discernibility matrix. That is actually very much about the rough set theory that I'm going to extract information from, that we can get some reduced amount of attributes. Then we could use that to help, or rather this reduced amount of attributes will be processed further by genetic algorithm, again in Rosetta, to come up with prediction rules that I've mentioned earlier on. So these prediction rules will be tested for its accuracy, for its performance. And when it's performing well, I'm going to now invoke the rule quality measure to actually further analyze the entire collection of the prediction rules to come up with one single association rule. That is very much what I'm interested in to have, to actually be used for the final system of expert system that I'm going to design later on. And I also use a decision tree to actually basically validate the performance of the data mining of the entire process, integrating the three strategies that I just talked about. And the decision tree is not found in Rosetta, it's only found in some other software, and I found one in Weka, So WICA, as some of them might have been very familiar with, it has data decision tree rather in WICA that we can use it to actually validate the rules that we have already discovered in the previous data mining strategies. And then, of course, if I mentioned, I'm going to design an expert system called Protective Relay Analysis System, or PRE, that will be using the rules that have been discovered to actually, the rules will be formed into an engine or knowledge base, the brain of the expert system, or PRE in this case. And this is designed using LabVIEW. And then we want to test the unknown relay. So this is the power system. This is the relay that I'm talking about, Arriva MICOM 411. Design, both are in PSCATs. So we have basically made a lot of changes in the library on the in the PSCAT. With the permission of PSCAT, we have actually communicated with PSCAT to allow us to do a tremendous amount of changes in the very simple distance relay found in the PSCAT. And we actually have managed to filed a patent, copyright patent rather, in one of the functional units, which is actually a power swing blocking function in the distance relay. You may find a detailed discussion on this modeling in this article, and these are some of the standards that I've used. It's actually those standards that are found in the manuals in Arriva that I've based on to design the relays. Some of the functional units that you can find in the relays, quite a number of them. The basic distance relay, other relays that underreach, overreach, supervision units, and then you have all other overcurrent relays, directional, non-directional, and then you have other supervision units like the pole data supervision units. You have pulsing blocking unit I talked about, and we managed rather to file a copyright, and some other supervision like reclosure supervision as well. So these are basically what you may find in the manual that we have managed to actually model as much as possible. And of course, what is very much of our interest is the event record facility that is found in the relay, the fault recorder, the oscillography, voltage current records, and of course the setting records. So this is the basic operation characteristic of face-to-face impedance measurement of the distance relay, the basic fundamentals of face-to-ground measurement of distance of impedance for fault involving ground, of course, right? And this is the operation characteristic of the face-to-face we call it face-to-face quadrilateral distance element. As you might have known how distance relay operates, we have zone 1, zone 2, zone 3. So it depends on the distance of how much coverage you are dealing with as far as the transmission system or the transmission line that this distance relay is actually protecting against the fault. Zone 1 is much closer kind of location of fault. Zone 2 is much further. Zone 3 is much further away beyond the next substation possibly, right? So what we want to see here, the trajectory. This is actually an impedance plot. So you are talking about impedance trajectory of the transmission line. So the impedance is measured, and when there is a fault, the impedance would immediately be going directly into where the zone that is of importance. For example, if it's located very much close to the distance relay, the fault, then it would definitely immediately go into zone number 1 because it's this very much very close to the distance. This is the position of distance relay. This line is actually showing where the direction of the fault along the transmission system. That is a face-to-face. This is a ground-to-face operation characteristic. Well, there are many other operation characteristics you may find in circular form. We call it MO and many others. But we are really interested in studying quadrilateral type of operation characteristics. So again, this is the operation parameters that are set in the relay, the actual relay, as well as the sorry. as well as the model relay. All right. Okay. Okay, this is again the KDD process. I'm not going to repeat that. And this is the data processing process that we have done from a very raw amount of data, complete data that we have extracted from the model relay. And finally, it turned out, it transformed into the type of data that is very suitable for data mining purpose. And this is the integrated operation of the rough set theory, genetic algorithm, and rule quality measure. The data that has been transformed is going through in producing rather the disability matrix, which is very much a characteristic of a rough set theory. And we turn and then find disability function. Those who are very familiar with rough set theory, these are the two things that you can run from with to have. And then from these functions, you want to actually solve the functions to turn it into something that very much of use, which in the end, what you would get, what you find will be reduction in attributes. In rough set theory, we call it redux. Redux is just a name that is given to represent how much the attributes have been reduced to a much manageable form. So with such redux, we will be producing the algorithm that we want to have out of the data. And we call it as prediction rules. So there are two ways of doing that. Method one is manually calculating the functions or solving the redux or the attributes, the reduced attributes. But of course, as I mentioned, it's very difficult. The data is so much difficult to actually deal with manually. So we invoke GA to actually help us in doing so. And finally the prediction rules, the algorithm. And of course, finally, what we want to really come up with is actually what we call as association rule. CD stands for condition and decision. So it's just a table where you have condition, you have decision. So the association rule is just one single rule that has been singled out of a collection of huge amount of prediction rules that have been discovered earlier on by RST and GA. So this association rule will be discovered using a rule quality measure. So this rule will be gathered by the protection engineer to be used as an engine for his envisaged space system to be designed. So this is just a repetition of what I've already mentioned in this entire flowchart. We're going to test the decision algorithm. This decision algorithm must be tested. So I'm going to test with, what we call as I'm not sure whether it's here. It's called cross-validation. Yeah, I'm trying to actually find the word. It's a cross-validation. I think this is very much familiar to most of us researchers. So from cross-validation, we want to find out how good the prediction rules are. We have to come up with results. So the result is actually presented in the form of coefficient matrix, and some other way of presenting, like area under curve of ROC, right? Okay, this is the expert system. How we design the expert system, the flowchart. This is the KDD process that we have done earlier on to come up with the rules. Then we extract the rules, we feed into our expert system. We populate the expert system with as much as rules as possible, depending on as many as faults that you can find in the power system seen by the relay. And then we do all these processes, and then finally do the validation. Remember, we are talking about when we are analyzing the performance of relay, we need to validate, and we need to also diagnose the relay, right? So the result we presented, I'm going to show you later how the results are presented. So this is the performance of the model relay in PSCAT of Arriva MICOM P441 for a fault occurring in is a phase A to ground fault over at 40 kilometer away in front of the relay. We call it zone 1, of course, because it's very close to the relay. You remember you're talking about zone 1, zone 2, zone 3. So when there's a fault, the trajectory of the impedance would immediately go into zone number 1. Of course, it would pass through the other zones to get to the zone 1. So this is the fault, the surge in current that has been basically plotted here. We understand there is a fault A to ground, and because of that, the relay is already, the model relay has successfully asserted and a tripping signal to a circuit breaker. So immediately, or rather with a little time delay after that, the circuit breaker trips the power system. And then finally, that's why you can see the power system will be removed. The signal, the current is removed because it has been disconnected. So only after a while, maybe because of there's a recloser in place, the power system is reclosed back into the system. So this is actually operating as what we really expected. So all in all, that's for one type of fault. You have so many other faults. So as you can see here, the relay has successfully operate according to what has been requested or required or called upon by the standard operations of the TMB's required standards. For example, for zone 1, it has to operate in 25 milliseconds. Yes, it did so successfully, very much less than that. It's only 0.5 millisecond. Sorry, I think it's, I think this one. Yes, 0.5 millisecond. And zone 2, the required time delay or time for the tripping to take place for fault occurring in zone 2 is 450 millisecond or 0.45 second. So ours is quite rightly so, it's 0.9 millisecond, right? And as far as zone 3 and 4, 3 seconds, and ours is only 3.5 minutes. So is good. It's good to go to actually for further application. So this is what we have done. We validate the detailed relay with that of the actual relay. We want to see how they relatively perform, the difference between them. This is the plot out of the actual protective relay in the actual Arriva. This is the actual Arriva P41 441. This is what we can plot if we extract the data from the relay. The current surge there, and then the fault, the tripping signal given out by the device. So we make a comparison. There's a TMB requirement I've already mentioned, 25 milliseconds for zone 1, and zone 2, 4.45 seconds, and 3 seconds for zone 3 and 4. So relatively, you can see ours, of course, is a model relay, has actually performed very much better than what actually has been shown by Arriva relay set. But unfortunately, if you can see here, the required, the performance is not as what has been expected by TMB. So at that time, we have a good discussion with TMB how they need to actually approach Arriva and deal with such a situation. Well, of course, TMB has their own actually lab to actually test all these brands of various type of relays. So one of them is, of course, Arriva. Nowadays, it's called GER stop. And this is the transform data that I talk about. So out of the 108 number of attributes from the raw data, we have managed to actually reduce to 46 by the transformation. This is not actually gone through the data mining yet, but we have managed to do some data transformation to actually reduce the data to only 46 attributes. And it's actually shown in the form of categorical data. It's no longer in a continuous. So that's why we need to transform. We need to pre-process the data so that this type of data in a categorical form is so much useful for data mining purpose. So these are the discernibility metrics that is very much a characteristic in Rashad theory. These are the discernibility function. So what we do is, okay, this discernibility function is actually taken out of this matrix. So we need to solve. This is called conjunctive normal form. We need to solve it to turn it into the disjunctive normal form. So what we do is that we simply multiply across all this junction over all the other disjunction cross over all this multiplication. So it's right. It's just like crossing multiplication of various terms here. So as you can see, it's not easy. It's just so difficult computationally. So it's called in the computer science NP-hard. So that's why we invoke generative algorithm. So generative algorithm has actually helped us in reducing the redux, right? Reducing the attributes into a set of reduced attributes we call as redux. So there are 4 possible redux, and what is actually of our interest is one of them, which is a redux number 1 for some specific technical reason. So we have chosen this reduced number of attributes. So you can imagine how much the algorithm will be understood by the protection engineers if we have actually reduced the number of attributes to only 1, 2, 3, 4, 5, 6, 7 compared to the earlier number of attributes of 46, or even the raw data of 108. So you can see, you can imagine how much actually RAPSET theory and generative algorithm has actually reduced so much in terms of the number of attributes. And then, okay, these are the 4 redux. Okay, the number of attributes, there are 7 of them. So of course, one of the reasons why I choose redux number 1 simply because the number of attributes have been very much reduced to only 7 comparing to all the other having 8 and 9. So what this is actually telling us, out of all these 4 redux, any one of them will be able to be used, okay, to basically alternatively reconstruct the data. So by just simply this using this number of 7 attributes, this would represent the exact characteristic, the exact behavior of the original data of 108 original attributes by just simply relying upon this number of reduced 7 attributes. So out of the 7 attributes, we can construct the prediction rules by superimposing the attributes over the original data. So the number of attributes, we just take some of the required 7 attributes to turn it into this collection of prediction rules or algorithm. There are altogether 120 rules for this one particular type of fault. And then the rules can be validated as using the cross validation tenfold. We break up the data, the rules of data into tenfolds, and then we test it to see how the prediction rules that we have discovered here perform. And of course, it has given out a very good, I would say, a reasonable amount of performance of 0.944. And another way of determining the performance is to find the area under curve of the receiver operating characteristic. As long as it's the closer it is, the area under the curve to 1, it would give us a good indication that the performance of the algorithm is very good. And then after the prediction rules have been tested successfully by one of these 2 methods, then we invoke the rule quality measure to finally let us find out the one single rule that of our interest, right? So this is the formula of rule quality measure. One of our particular interest is one of the methods in rule quality measure called G2. It's called G2 likelihood ratio statistics. So this is the formula. So there's a threshold that we need to set to finally discover out of the 120 rules, only those rules that are of our interest. So out of 120 rules, we have actually reduced to a much reduced amount of rules by invoking the G2 statistic or rule quality measure. And then we go even further by taking all the rules with all the processes, by conjuncting all the rules, by using the concept of Boolean function manipulation, by applying conjunctive idempotence rules. So we finally come up with this one single rule that are very much of our interest. So this is the rule that we want. and we are only using 7 attributes. So what this is saying is that because it's being tested over the A to ground fault at zone number 1, so you can see these are just this is the original 46 attributes, right? So one of the attributes, which is this one, or the 7 reduced amount of attributes, is there is this functional unit that is called detection unit of phase to ground fault, and this is given as a value of 1, zone 1. Of course, 1, 2, 3 meaning because the impedance trajectory has to go through 3, 2, and finally into 1. And then at that point of time when the fault is occurring, of course the breaker is still closed, and all these other behavior of the internal functioning units of the relays, and finally is giving out tripping units, tripping signals. So these are conditions. This is the decision. So if we were to actually compare with the original data, this original data, it actually really strikes us some interesting point here. So this is what we can compare with the rules. This single rule that I've already discovered is that if you try to superimpose this rule over the original data, it really actually brings us about only those attributes that of our interest that have been underlined here. So this is where actually validates the idea why rough set in combination with genetic algorithm and root quality measures are very useful to deal with this inconsistency in our data. You can see here, the conditions are all the same at one particular point of time, and then in the next time step, suddenly even with the same decision conditions, the decision is different. So if we were to be able to actually analyze manually, we would find it difficult. We would find it difficult to really understand whether it's really a tripping thing, because at one point in one of the time step, the conditions are there, but there's no tripping. So this is where actually the data mining is actually help us in finally find out this rule. So once that is completed, we do the same thing for decision tree algorithm, right? So this is the strategy in decision tree. This is a strategy in rough set theory. We have disability matrix. We have this formula. Finally, that we extract to finally turn it into decision algorithm. We can also do the same thing using decision tree. Decision tree can also come up with assertion rules. And we compare the performance of both rough set theory based and decision tree based. And finally, we come up with the comparative results of both techniques, the prediction performance of the rules, the prediction rules. They are quite close, right? For using the confusion matrix, as far as the area under curve is also very much close to each other. All right. So now, having to actually understand that both techniques have given us the rules that we want, the succession rule. But why do we are so much interested in rough set? We look at it something that may sound to be very complex because we are actually integrating with GA, we are integrating with a root quality measure, whereas decision tree is only on its own. But the thing here is that you see here, if you compare these decision rules with those that we find in rough set theory, you can see the conditions are very much complete comparing to those that we see in decision tree, the decision tree results. The conditions are so much simple, too concise, very concise. So in the end, in protection engines would actually find it very uninteresting because decision tree has given us lacking information. Okay, the information is so much lacking in as far as giving us a good understanding what has actually really occurred in the device. There are only two conditions here, but if you compare it to what we have used, the rough set theory is given us quite a detailed kind of, we call it antecedents or conditions in order to finally for the relay to actually give a tripping signal. So this is very much comprehensive as far as the rules is concerned and very much informative as much, as far as for the good understanding of the protection engineers. So if we were to compare between these various, these two strategies, the Rosset theory based and the decision tree based. So you can see how different the rules are. So the one that we have just seen is just for one particular fault. If you did for all the other faults, you can see similarly the rules that are discovered by Rosset theory base is very much complete and more informative compared to decision tree. So in the end, what we want to do is that we want to extract the association rules, and we want to populate the expert system that we design using LabVIEW here one by one. So what we do is just connect this protective relay analysis system or expert system, in short we call it PRE, connect it with the data, the file that we want to extract the rules of this Rosset analysis that we have done, and we populate this field. So these are basically all the rules, all the conditions, and the decisions that you can exactly match with this one for one particular type of fault. So next, we want to validate the rules with those relays that we want to test on to see how good the unknown relay has already performed. So we link to the unknown relays file, and it was actually discovered that a fault has already occurred, A to ground fault, in zone number 1, and it's scoring somewhere around 38, 39 kilometers away from the distance relay. And it's actually rightly so. The relay has successfully operated, is validated. So it's a validation field. Breaker A has already tripped accordingly, correctly. The relay has actually tripped in 1.2 millisecond, and it's very much compliant with the required TMB time of 25 millisecond. The circuit breaker operating is 46 millisecond, and all in all, the overall time taken to actually finally clear the fault is -2, which is 47 milliseconds. So if you were to actually see how actually the relay has behaved internally, looking at all these various functional units, what is actually done by this expert system is that comparing these rules with the whatever data that has been extracted from the unknown relay, it is actually given us some information on things, how actually the functional units have actually behaved. So in one of them, for example, one of the units, like for example, overcurrent supervision unit has correctly operated to actually detect zone A, for example, and it's okay. Okay means it's functional. So finally, when all conditions are okay, finally we would expect the tripping signal to be given out by the relay to be okay. So this is a validated operation kind of a relay that we are testing on. So we can reconstruct from the data that we've got from the relay to see how actually the relay behave in as far as plotting back again the voltage and current, and see how the internal function of the relay behaves. See, the relay has managed to detect a fault, and the tripping signal has been, a signal from circuit breaker has been given into the relay to tell that tripping has taken place. So that's a good relay. So what about a bad? Okay, we are still on the good relay. A good relay. So this, if you were to actually use again, we are still on the good relay. Healthy relay in that sense. If you were to actually plot the operation characteristic and see how the trajectory of the impedance is actually behaving, okay, we are talking about ground to phase A to ground fault. Of course, for phase to phase, you wouldn't be able to actually see the trajectory to be intruding the zone. So we need to look at the phase to ground fault operation characteristics. So it's rightly so that we would, as we expected, one of the phases. So this is phase A, maybe phase B, phase C, and phase A. We can see since it's phase A to ground fault, we can see that it's actually encroaching zone number 1 as we expect. So this is what we want to see when we are talking about the healthy relay. So what about the unhealthy relay, a failed relay? So of course, is validated, or rather is been basically confirmed that no tripping has occurred, even though the fault has been detected. Also, again, this fault is actually detected out of the data within the relay itself. The measured impedance within the relay itself, the model relay in this sense. So the relay has failed to operate. So of course, no timing is recorded. And if you were to actually compare the rules with the whatever event report or the data that's resident in relay, so this distance ground distance relay has failed to operate. And finally, at the top level, we see that the tripping signal has not been able to be given out to the circuit breaker to actually trip the circuit breaker eventually. So this, what we do next is just tick any one of the field indication and see what has actually occurred, what kind of symptoms that we can read from the situation from. So what if you do that, we trip this overcurrent supervision unit, the function unit, one of the tens of functional units within the relay. It is told that the ground distance overcurrent supervision setting of zone number 1 may not be correct, may not be correctly set. Okay, so the setting might not be correctly set. That's why it's actually has given out the failure in as far as the operation of the relay. So we do that by clicking this and find the system. There are many possible symptoms that I've actually written behind the screen, behind the scene rather, of this expert system to actually help us in understanding the kind of symptoms. So in conclusion, we have actually finally managed to hypothesize, understand the operation relay by using this integration of Rorschach theory, genetic algorithm, and root quality measure data mining strategy. And of course, we have so many other computational intelligence based research in as far as protection system, like for example, rough set base for understanding the operation time of relays. We have also used some signal processing and neural network to understand the islanding detection technique. And we have also used some other type of signal processing to, again, similarly understand the islanding detection strategies. We have also used support vector machine and some signal processing to really find or diagnose a fault occurrence in a power system. We have also used some other computational intelligence to actually find to help us in dealing with the differential protection in power system, coordination of overcurrent relays in power system, right? So we use genetic algorithm, and we have used a combination of some wavelet signal processing with NFIS, right, to deal with the high impedance fault. High impedance fault is something very peculiar to us because relay of how good it is has been said, it fails to actually operate because of the low current that is detected by the fault, by the relay when the impedance fault is in place. So, and we have many other works that we have done in as far as using computational intelligence in dealing with the power protection system. So with that, I pretty much end my presentation. So I would really like to actually pass back the floor to our sister Tasmia. Thank you very much.
Thank you so much, Dr. Lutfi, for this wonderful and very informative presentation. The application of data mining in predictive relay is really very intriguing and inspiring. Thank you so much for sharing your knowledge with us. Now, we shall begin our question and answer session. I'd like to request all the participants to ask their questions to our respected speakers via the comment section. I'd like to invite Dr. Jason to join as well. Thank you.
Hi. Okay. Thank you for the questions, Professor
Uh,
Dr. No Ashida.
yeah, the
Okay.
first question. The first
Do
question
I?
is to Dr.
Yeah.
Jason. Yeah. The question is, according to some research, Monte Carlo technique accuracy is low. Can you comment on that? Is it still
Okay.
relevant to use MC to perform reliability assessment?
Okay. So Monte Carlo simulations, the accuracy is undoubtedly low initially if you did not run enough numbers of simulations, the number of iterations. So that is the reason why in power system studies there is a criteria on the minimum numbers of simulations that we have to perform, and that is determined by the what I call the convergence rate of a particular index that has been agreed by the research community. They use the expected energy not supply as the benchmark for convergence. That is when the coefficients of variations of that index, the abbreviation is EENS. So when the coefficients of variations of EENS is below 5%, then the result is generally accepted. ENS is particularly selected because it has been shown to converge the longest. I mean, take the longest time to converge. Therefore, when EENS converge, then um, it is expected that other indices have also converged. So that is how we ensure that the Monte Carlo simulations performs the right simulations accuracy. Yeah.
Thank you, Dr. Jason, and thank you, Dr. Noor Ashida, for this question.
Do I
The
go
next
ahead and answer?
question is
Yeah.
also Dr. Noor Ashida. For your study on, it's to Dr. Jason, for your study on NTO, DPR, and BSS, are you using the IEEE test system or the real system data?
I'm using the IEEE test system, in particular the IEEE 24 bus reliability test system. That is, I think, quite popular. On top of that, I also use the extended version of it, which is the combinations of that system three times to form a multi-area larger network to represent a practical situations. Yeah.
Thank you, Dr. Jason. Thank you, Dr. Noor Ashida. The next question is for also Dr. Jason from Mr. Hazli bin Muklis. What type of technique you use to solve the optimization problem in your work?
Okay. I think Prof. Hasli is also an expert in these simulation studies. Yeah. I myself in this particular work, me and my colleague, because this is a work that I'm currently working with one of my research partner in Taiwan. So he is using Cplex, right? Cplex as the optimizations to solve the optimization problem. So I don't use Cplex myself, but he has the access for that, and I am collaborating with him on this aspect. So we are using Cplex to solve this optimization problem.
Thank you, Dr. Jason. Thank you, Dr. Hasli. Next question is from Mr. Manoj. Good morning, all interesting topic. This is a question to Dr. Lutfi. Can big data be employed to aid the data management process?
Yes, thank you very much, Mr. Manoj. Yes, nowadays we are very much into this idea of big data. Of course, if you are talking about big data, you are dealing with so much amount of data, very much larger than the data that I've been dealing with. So because you are talking about enterprise amount of data, so much of data. So if you are dealing with wide area kind of protection system where you want to understand the operation, you want to understand the performance of protection system over a much larger area, then of course big data can be basically so much data, and big data comes along with so many data mining strategies. Data mining strategy is just an aspect of data mining. you may invoke any type of data mining strategies to actually aid in as far as data management process is concerned, to give an idea how the protection system has actually behaved, and also maybe it can help you to actually expect how should the protection relay actually behave out of this big data analysis. Yes, big data can be very much helpful when the data gets bigger. Right?
Thank you, Dr. Lutfi. There is another question from Mr. Manoj. Can we maintain and ensure the integrity of data during data mining process?
It depends on the data, right? It all depends on data. If the data is reliable, so data mining is just a process. It helps you to actually deal with the data and actually provides you with the knowledge. So if the data is bad, of course, the knowledge that you might be given, maybe what is reflected of the data. So that's why when we do our research, we want to, as much as possible, to make sure that the model relay is actually as close as possible to that found in the industry. So that's why we have studied the manual, the operation and maintenance manual, and we actually refer to expert from our utility company, we call it TMB in Malaysia, to make sure that finally the data that is registered, that is actually stored in the relay, will be something that is reliable, something that we can use. Because why? Because we want to make full use of this data to finally churn it out, do a data mining out of it, so that the results, the knowledge that we can gain is really reliable. So that's or rather making sure that the integrity of the data is maintained throughout the entire data mining process. So it depends on the data. It boils down back to the kind of data. If the data is bad, of course, whatever result you get may be good, depending on the data.
Thank you so much, Dr. Lutfi.
Okay.
The next question is, what are the
Okay.
potential future works if any researcher interested to do similar work in this data mining and in the presentation in this area that you worked in?
Okay, thank you very much, Prof. Hazli. First of all, I would like to really thank personally Prof. Hazli, because you are the one who actually invited me to be the speaker in this talk. So, okay, there are so many potential works. I'm just dealing with distance relay. If you're talking about protected devices, you have so many relays. You have overcurrent relay, you have diffusion relay, you have you just name it. It's just too many to actually list down. And that's about protective device. If you are talking about like fault locator, you're talking about sequential event recorders, fault recorders, recloses, all these numerical microprocessor-based device where you can find data in it. You can actually do so many things. You may actually repeat the whole process that I've done, but now you want to understand an overcurrent relay operation. So that is in device level. If you are talking about system-wide level, you may actually do the same thing. You just get data from as many devices as possible, as mentioned, IEDs we call it, intelligent electronic devices, and we actually do the data mining and see how the entire power protection system is actually behaving. Nowadays we call it SPS. What we call it as SPS stands for protection system. I'm just lost of words. Actually, it's not a conventional type of protection system. It's more of designing your protection system, a smart protection system, to actually come up with a solution by just getting data from all these devices. For example, if you want to make sure that there's little power loss, you want to deal with voltage drop, for example, of a certain line, so you need to get data from all these devices. So this SPS will be able to actually design in such a way to actually help you to decide how to make sure that there's no voltage drop, there's not much of a power loss within a line. But this is not a conventional protection system in overcurrent, in distance. It's more of a SPS. I just lost words. SPS, power is a smart power system or a special power system, something like that. Or remedial power protection system. Yes.
Thank you, Dr. Lutfi. Our next question is from Mr. Hafiz Idris. The question is to Dr. Jiyashan. With the operation of circuit breaker based on optimization of the network topology, how the operation of circuit breaker being conducted, manual or automatic? Because normally the operations of circuit breakers are conducted manually by the operators or automatic by protection relays when fault occurs.
Okay. I did not mention in just now my presentation slide is that the study that we are performing is a day ahead scheduling studies. So meaning that we do a planning 1 day ahead. So we do based on forecasted weather data and forecasted load demand. So with that kind of stress and that kind of situation on the network, then we want to see how can we best mitigate the congestion. So so in the day ahead planning, then the simulation time constraint is not a problem. So and then when we have decided on an optimum solution, then we can close or open a particular connections manually or automatically. So by automatically, I guess the person who asked the question means that we control it through computer, right? Through a particular mechanism. So I'm not expert in this circuit breakers operation. Probably Dr. Lufti will be able to answer on how circuit breakers are normally operated. So I believe that circuit breakers, there are some are huge and some are small. So maybe the smaller one can be performed manually. But I believe we are going towards automation nowadays. Yeah.
Thank you, Dr. Jason. The next question is for Dr. Lutfi from Mr. Hafiz Idris. Is that the expect system suitable for all the relays installed in the grid? Because we know that the configuration and the setting for each relay are designed based on that relay location and network configuration. The relay at different location might have different response.
Yeah. Yeah, but you're quite right. You're very much correct in that sense. Well, that's the basic understanding of actually how we should have the relays operate. We need to really understand the topology, the configuration of network system before we can finally set the relays. Because simply setting relays over a particular configuration that is not really in place in the real power system, it can be disastrous. That's why, as I've said in my talk, topology keep changing. Especially nowadays, you are talking about microgrid. You are talking about distributed generations that have basically imposed some difficulties in the operation of relays. Especially when we are talking about in-feed. When you have distributed energy resources, it introduces some additional amount of currents. So in as far as the distance relay that I just talked about, it would be very difficult for the distance relay to operate correctly if you base its operation. Of course, you have set the relay operation based on the original topology. And then after some time, the renewable energy resources come into place. So this in-feed has actually failed, has failed the relays, because the amount of additional currents would basically make the measured impedance to be much lower than what you have already set in the first place when the topology was not disrupted or not, I would say, tempered with by having this microgrid or distributed generation. So again, going back to your question, you need to possibly go back to the setting of the relays and restudy the topology and set accordingly. And nowadays there are many research in that directions. We call it adaptive protective relays, in the sense that the relay will be able to actually self-adapt to be adaptive enough to be able to change the setting by itself, in order to reflect, to mirror what the topology has actually changed to now. So there are many research in that directions too, right? So of course, yes, you have to really understand the topology. Yeah. All right.
Thank you so much, Dr. Lutfi. This is from Dr. Farid. How this data mining being embedded in the real protection relay?
Okay. So the work that I've presented is about basically eventually designing an expert system. Is an expert system outside the relay, where you can retrospectively test the data of the relay, of relays that have already operated or misoperated. Well, data mining can also be used in many other ways, not necessarily in discovering rules so that finally you can design an expert system. You can also embed, as Dr. Farid mentioned, data mining within the device itself, within the relay device itself. Because it's an intelligent device, it's a microprocessor based, it's just like a computer. You can design a data mining within that device to actually be able to decide the kind of solution for whatever faulty situation that comes about by the relay. So we are talking about algorithm. So most of the industrial algorithm are all mathematically designed. Like what I've seen you, the characteristic of impedance of measurement is all mathematically designed. You may actually substitute this algorithm with a data mining. You can use data mining. Why not? Data mining can be run real time, no problem. In some of them, very powerful. So, yeah, you can do that. As far as I'm concerned, as far as our group research is concerned, we have not gone in that direction yet, having to actually embed data mining within a specific device or protective relay. This is something we have thought of to actually embark on, to actually expand our research in involving data mining within the device itself. Okay, all right. Thank you.
Thank you so much, Dr. Lutfi, and thank you so much, Dr. Jason. That's all. That's all of the questions for today about this session. So now I'd like to pass it over to Mustaqim. He will proceed now. Thank you.
Thank you, Sister Tasmia, for handling the floor. What a detailed, accurate, and resourceful webinar today, as well as interesting Q&A session. I think we all had fun for webinar today. We have reached to the end for today's webinar session. I would like to thank you everyone for joining us for today IEEE PES Malaysia Research Discourse 2021 webinar session. Don't miss the next webinar. They will be held next week on 18th September. I hope you achieve what you came here to achieve. Thank you for coming.
Thank you.
Bye.
Right. Thank you very much, guys. Right.
Thank you so
Thank you
much.
very much
Thank
for
you so
having
much.
us.
Right. Right. Thank you, Tasmia. Thank you, Mustaqim. And thank you,
Thank you,
Dr.
Doctor.
Lutfi. Yeah.
See you
Thank you,
again, Dr.
Doctor.
Jason, Tasmia,
Right.
Mustaqim.
Yep. See you again, everyone.